a talk on research and Raman effect at length. Don't take much time. I welcome all of you and especially hearty welcome to Malesh sir. Welcome to you, sir, for this session. Now I welcome Dr. Abhishek and my colleague Mr. Umesh to this webinar. I request my colleague Mr. Umesh to give a brief overview of the experience and expertise of Professor Malesh sir on this occasion to all of you. Please take over, Mr. Umesh.
Thank you very much, sir. Indeed, we welcome you also, sir. Before starting the technical session on about Sir C.V. Raman sir and on Raman effect, I would like to introduce Dr. K.S. Malesh sir. Currently, Dr. K.S. Malesh sir is a retired professor of physics from the Department of Studies in Physics, University of Mysore, Manas Gangotri. Sir has qualification in PhD in theoretical physics and has experience of 12 years of teaching for BSc students and 25 years of teaching for MSc students, along with 30 years of research. Sir has guided several PhD students and also published 20 plus research papers. And his area of interest are quantum mechanics and its foundations, polarization optics, and group theory. With this brief introduction, I welcome you, sir, once again to deliver a talk on Sir C.V. Raman and Raman effect. Also, I welcome Abhishek, our CEO, Dr. M. Ramesh, and other participants also. Thank you, sir. Over to you, sir. You can start.
Good evening to all the participants. At the outset, I would like to thank CEO Sri Ramesh, Umesh, and Abhishek for giving me this opportunity. And I also welcome all the viewers. I will be talking about Sir C.V. Raman and Raman effect on this 132nd birthday of Sir C.V. Raman. And this day also happens to be the birthday of Marie Curie. So I begin my talk titled Sir C.V. Raman and Raman effect. Am I audible to all of you? Can you see my first slide?
Yes, sir. You're audible.
Yes, thank you. If there is any problem, please interrupt, and I hope Abhishek can help me. This is my just 10 minutes ago, I ended my preparation, therefore I have not even done a rehearsal. Let me begin with this. Sir C.V. Raman, Sir Chandrasekhar Venkatraman was an Indian physicist. He was awarded the 1930 Nobel Prize in Physics. He was the first Asian to be awarded a Nobel Prize. And I am also right, he is also the first and only resident Indian to have got this award in science. Of course, Rabindranath Tagore also got for literature, but Sir C.V. Raman got it for science. The award was for his work on the molecular scattering of light and for a discovery which has become very significant. And this discovery is named after Raman himself. So Raman effect. Most of you and all of you know what Raman effect is. So I will be just touching on certain aspects which highlight the intellectual side or the research side of Sir C.V. Raman in the next few slides. Raman was born on 7th November 1888 in Thiruvannaikkaval near Tiruchinappalli. His father, R. Chandrasekhar Iyer, was a school teacher when Raman was born, and mother was Parvati Ammal. Parents had 8 children, 5 sons and 3 daughters. Venkatraman was the second child. Father became a lecturer in mathematics and physics in Avian College at Visakhapatnam, Andhra Pradesh. So at a very young age, Raman had to move to Andhra Pradesh. He had procured an excellent collection of books on physics, mathematics, and philosophy. Raman's father had collected. Maybe that helped Raman to get more interested in physics. Also, Chandrasekhar Iyer was a great lover of music and played the violin extremely well. So it may not look strange why Sir C.V. Raman got into, in the blood of C.V. Raman, music also was there, inherited from his father. So you are able to see Chandrasekhar Iyer and Parvati Ammal in this slide. I move on. So in this map, you can see this Tiruchirappalli, which is now called as Tiruchirappalli. And this is the house where he was born. So colorful. So indicating, what Raman did later. Maybe it is representing that also. Young Raman was a brilliant student. In fact, somewhere I read he was a child prodigy also. Raman passed his matriculation examination at the age of 11. Passed his first arts examination equivalent to today's intermediate with a scholarship at 13. At 13 years of age, he passed his intermediate. Maybe we would have been in 8th standard or so, 7th or 8th standard when we were of this age. He passed his BA in 1904 at Presidency College in Chennai at the age of 15. Passed MA in 1907 at the age of 19. All this I am saying is just to highlight that as a young student, he was already ahead of his studies. In fact, his lecturers used to find him too young but also brilliant. So, in fact, he won all the prizes in his BA and MA examination. Left no prizes to anybody. And his teachers even exempted him from attending science classes because I think he knew all that they were going to teach. Raman's first paper was when he was just 16 years old. He was doing a routine experiment on his college spectrometer and he observed some diffraction bands. A deep study of this led to his first paper. The paper is titled Unsymmetrical Diffraction Bands Due to a Rectangular Aperture. It was published in one of the most prestigious scientific journals of that time, Philosophical Magazine, Series 6. This is the reference. So, placing a prism on the table of a spectrometer, the slit of the collimator was viewed after reflection by prism surface. As you can see here, there is a slit here at the collimator. Light from that aperture of the collimator falls on the prism here. This is almost normal incidence. So you are seeing from this reflected light here. You could also orient your prism in such a way that the incidence is not normal. The normal to this surface is along this side. So this is oblique incidence. So normal and oblique incidences can be arranged, and that's what Raman did. For large oblique incidence, the image of the slit broadens into a diffraction pattern, as he saw here. This is the picture of what he saw. So with increasing obliquity, diffraction pattern progressively changes in character and becomes unsymmetrical. So as you can see that the diffraction pattern on one side is different from that on the other side. So this was what Raman observed when he was just 16 years old. So my photograph here is only indicating that he was always an observer, a keen observer. So at his young age, he wrote his first paper when he was 16. The curvature method of determining the surface tension of liquid was the second paper by Raman. This also got published in Philosophical Magazine, 14th volume, in these pages in 1907. Raman suggests here that the surface tension of a liquid can be found out by measuring the curvature of the drop formed at the mouth of a glass tube. But I took I wrote this diagram looking at one of the references. So this is the glass tube where, say, some liquid is filled, and this I am only showing you the drop here. So this is the curvature of the drop. And if you consider a coordinate system here, the y-axis and x-axis, so Raman said that if one can measure the curvature of the drop formed at the mouth of the glass tube, if you can measure the curvature at these, especially at the point where it is at the origin of the coordinate system here, you can find the surface tension of that liquid. Since it is difficult to measure the width x comma y on a drop, so it is not so easy. Where there is a drop, and how can you measure the distances from one end to the other end, as you can see here. So what he did was he sent arc light from an arc on this drop and made, he got the shadow of this on the other side, and he measured the distances using that shadow. The method described in this article gives results which are fairly self-consistent, rather. It should have been consistent, not self-consistent. That means they agreed with the values. If I remember correctly, what he got was some 77 dynes per centimeter or so for water. Because of the difference that he got from 77, I think the standard value is around 72. Because of this difference has not yet been found and is under investigation. This is what Raman says. I took the sentence from his paper to indicate that he is not hiding anything. Raman is open enough to say that he has not got the exact result, but consistent result. And he is also saying that he is not able to find the cause. So he is revealing that here. So that indicates he was a true scientist. At an young age, Raman's interests were in books. He liked, as a student, the Sensations of Tone, English translation of Helmholtz's book, and on geometry, the Elements of Euclid, and also the book The Light of Asia by Edwin Arnold. On the moral side, what moved Raman most was one of the incidences in the story of Siddhartha. So he says that, Raman himself says, I remember being powerfully moved by the story of Siddhartha's great renunciation, of his search for truth, and of his final enlightenment. So in these words, I think you can see that Raman's interests were also for the search for truth and to get the final enlightenment of whatever he was studying there. So after his studies, lack of research and opportunities in the country and unwillingness to go abroad made Raman enter into or take up the FCS examination, the Government Service Examination. He became Assistant Accountant General in Calcutta. He also married Srimati Lokasundari at that time. Just to give some more information, his salary was around rupees 400 at that time, 1907 or 8 or so. The amount was very sizable at that time, and that 400 included marriage allowance of rupees 150, which means maybe his salary was rupees 250, and since he was married at that time, he got additional allowance of 150 rupees. Lady Raman seems to have quipped that Raman married her to get the marriage allowance also. So you see that Raman stayed in the country. He did not think of going west. Rather, he went eastwards to Calcutta, to West Bengal. Instead of science, he chose government service. So, I mean, had he continued like this, the country would have lost a great scientist. If some miraculous thing did not happen, that miraculous thing was not that extraordinary. It was as common as you look at a board when you're walking on a street. Raman too, one day while he was going to office, he saw a board inside a compound in the Beau Bazaar street in Calcutta. He was going by a taxi. The taxi was called taxi, although it was a horse was pulling the vehicle. So while going there, he saw this board, and this board read Indian Association for the Cultivation of Science. This association was built by Mahendralal Sarkar. He founded this center to encourage pioneering research in science. Raman entered the building and met one person called Ashutosh Dey. This opened a new chapter in Raman's scientific career. So Ashutosh Dey took him to another person, nephew of Mahendralal Sarkar, and introduced to him. Actually, Ashutosh Dey later on assisted Raman for nearly 25 years in his life in that building. So Raman met Amritlal Sarkar, nephew of late Mahendralal Sarkar. Amritlal Sarkar was waiting for somebody to revive the science activity. So this was built by Mahendralal Sarkar to encourage scientific activity. So after Mahendralal Sarkar, Amritlal Sarkar took care of it, but he was finding nobody to do activities. In fact, when Raman went inside, everything was kept in such a condition that no instrument was used or all dust collected on several instruments. So Raman saw this office or this center in such a state. This opened a new chapter, as I said. Raman did significant research in this center, Indian Association for Cultivation of Science. Raman soon was recognized for his research. Look at this person. He is an assistant accountant general. He goes to office during the office hours, and after office hours, he would be found in this building, and not any university center or anything like that, but goes on doing research in various aspects, and soon he gets an international recognition for this. So Raman worked on various aspects of the vibrations of strings, such as the maintenance of vibration, the onset of resonance, etc. He also worked on the sound patterns of heated metals. He became an international expert on sound and musical instruments. I have shown to you here some diagrams from G. Venkatraman's book. So, G. Venkatraman's book, which I have referred at various places, including borrowing these pictures. So, here is the Veena as designed for the experiment, right? So, this is that Veena. These are the Mrudangam surfaces where you can see particles arranged in patterns when the drum was vibrated, and certain modes of vibrations, and later on some computer graphics recently or sometime back, I don't know when this was taken, but all these indicate that Raman, or they represent the kind of work Raman did at ISCS. Professor Ashutosh Mukherjee, Vice Chancellor of the Calcutta University, requested Raman to accept Polite Professor post in the University of Calcutta. Raman left his lucrative and prestigious government job to enter university for half the salary. I think one must take note of this attitude or this person, Raman. And the only other thing that comes to my mind is even Feynman, when he was invited by one university, the invitation was something like Professor Feynman, if you come to our institute, we will double your salary or we will give double the amount what you are getting. Feynman seems to have rejected by giving answer that if you double my salary, my wants and wants of my family also get doubled and that won't serve any purpose. So Raman also, his love for science and research in science was so much that he left his government job and came to university. In this career, he also became the honorary secretary of the IACS. So he actually worked in two laboratories, in his university as well as in this IACS. During these years, Raman went abroad, and in every visit, his inquisitive mind helped him crack some interesting problems. Raman and Sutherland did some experiments in St. Paul's Whispering Gallery. So when he went abroad, he visited the center and concluded that Lord Rayleigh's explanation was not complete. So Rayleigh figures a lot in the studies Raman also made. So almost in all his research studies, Raman examined Raleigh's suggestions and Raleigh's conclusions. And during his one visit here, he goes to this gallery and makes some experiments there, taking their permission, and concludes that whatever Lord Rayleigh has said, accepted certain aspects of Rayleigh, but showed that not all that Rayleigh said was right. So this work, along with Sutherland, is reported in Nature. So the blue of the sea was another phenomenon Raman explained as due to the scattering of light by water molecules. So this also happened during his voyage. He did experiments on board during his sea voyage and showed that it was not merely due to reflection of skylight, but also due to scattering by water molecules. In fact, he did experiments on the ship. He carried a direct vision spectroscope and also nickel prism and all that. So I think I have some more thing to say here. Raman studied the light from seawater. So Raleigh's idea was that the sea appears blue because it is just reflecting the skylight. What Raman did was he used a nickel polarizer, and by orienting the nickel polarizer, he was able to remove the skylight reflected by the surface of water. So even then, even after removing the skylight from the surface of water, the color appeared to be blue. In fact, he found that light coming purely from sea was indeed blue. He attributed this to the scattering of light by water molecules. So this looks like a beginning to his great discovery later. So the color of the sea, he said that he attributed this to scattering of light by water molecules. In fact, he also was able to see that the sunlight was penetrating into the seawater up to certain depth. And regarding that also, he made a study and said that diffraction effects could be taking place there. Of course, Raman later explained the blue of the sea using the fourth power of frequency dependence formula of Einstein-Smoluchowski. So Einstein and Smoluchowski had given a formula for liquids in which the density fluctuated, and because the liquid molecules are moving, so they had obtained a formula for the scattering of light from that, and that formula also contained the fourth power dependence, as in the case of Rayleigh. So for atmosphere, so what Rayleigh did for atmosphere, Einstein Smoluchowski also did for liquids and had got a formula using which, or later, Raman said that his reason for the sea to be blue in color from his studies agreed with, more or less qualitatively agreed with, Einstein Smoluchowski's formula. Raman and his students made a lot of studies on scattering of light in solids, liquids, and vapor. So you can see in G. Venkatraman's book a variety of studies being made. They were all the time wondering that some mysterious radiation was coming. I'll come to that. Raman became more interested in these studies. Around that time, Compton reported scattering of X-rays. So in which, as you know, the wavelength of X-rays change due to scattering. So Raman felt that if X-rays, which are also electromagnetic waves, undergo change in wavelength, can't the same thing happen in the optical region? Right? He suspected that there must be an optical analog of Compton scattering, which means that even visible light should undergo change in wavelength. Raman's group found, in addition to Rayleigh scattering and fluorescence, a new type of scatter radiation, polarized and frequency change. So this was the study made by Raman and his group. In fact, this was personally observed by Raman along with K.S. Krishnan on 28th February 1920, which is the famous discovery that Raman made. Look at this diagram. So if you consider Rayleigh scattering, what happens is when you send green light and observe in a direction normal to this, you see the green again. So this scattering is called Rayleigh scattering, where there is no change in wavelength. So this, of course, also accounts for the blue of the sky. Whereas the process of fluorescence, what happens is, say some light, green color light, you send it to certain substance, this green light is absorbed, and after some time you see that a weaker wavelength, or rather some red light appears. So this is the well-known fluorescence radiation. In their studies, what happened was when green light was sent, not only green light came, but also red light came. This was not as the case of fluorescence, because in fluorescence, the light came was unpolarized. But here in what Raman's students and Raman did, the radiation had a different wavelength. So the incident radiation underwent wavelength change and was also polarized. So this way it was different from fluorescence. And this was the effect which brought Raman to light. So this great discovery was announced by Raman on 28th February 1920. Raman effect was later studied more precisely. Here is an arrangement where Raman effect was studied. This figure is from G. Venkatraman's book. Mercury arc was taken. Even getting incident light was not a powerful incident light was not easy at that time. Initially, Raman's group did work using sunlight, and they had a motor, which because of which, I mean, in order to have a stable beam, right? They had kept a mirror, and the mirror was continuously getting deflected through a motor arrangement. And all their experiments were initially with sunlight. Later on, they used this mercury arc. So you take mercury arc, light from mercury arc contains all the wavelengths of mercury, put a filter and some additional uranium glass sheets and all to get a very narrow beam of monochromatic light, and then focus it on some incident, on some organic liquid. This incident monochromatic beam gets scattered in some direction like this, perpendicular to this scattered beam contains wavelength other than this, whatever came here. So just put a filter for this whatever wavelength you got here, you get that color also. You put another filter, so some other color also came. So the later on studies suggested that what actually happened was the scattered radiation fell into three groups. Green color coming as green color. This is only indicative of what happened there. So this is the unmodified light having same frequency as the incident light. And there were lines which had higher frequency and also lines which had lower frequency. So spectral lines with frequency less than the incident frequency are called Stokes line. So such things happen even in fluorescence. So the name Stokes lines is taken from the discussion people used to earlier refer to fluorescence. So these are Stokes lines and these are anti-Stokes lines. These are spectral lines with frequency greater than the incident. Their number and intensity was less than that of Stokes lines. So these Stokes lines were more intense. They had many lines in that band. However, here there were less number. So as you can see in this graph also, right, the intensity graph, there were more lines on the Stokes side, less on the other side, and even the intensity of these slow compared to the Stokes line. And you know the reasons for that. So let us come to the theory of Raman effect. This was the effect which brought him the Nobel Prize. Raman effect involves a material medium and electromagnetic radiation. So you need a material medium and also radiation. Theoretical study can be done in three different levels. One is the classical theory. Second one is semi-classical theory and quantum theory. Classical theory consists of the following, that both the medium and the radiation are treated as classical systems. So the medium consists of oscillating charges. The incident light is treated as an electromagnetic wave with electric and magnetic field. These electric and magnetic fields, while passing through the material medium, they influence the medium and cause electric and magnetic multipole moments. These moments then radiate and lead to scattered radiation. So one can classically consider this Raman effect, and this classical theory can explain the frequency dependence, why there is a Rayleigh part and why there are Stokes and anti-Stokes, etc. However, if you want to go beyond this, classical theory cannot be used. So the next level is the semi-classical theory. In semi-classical theory, medium is a quantum system, field is a classical system. Which means medium consists of molecules. Molecules have, as you know, rotation, vibration, and electronic energy levels. The interaction between the electromagnetic wave and the medium is treated as perturbation here. So as electric fields pass through the molecules. So you see there can be electric dipole interactions, magnetic dipole interactions, and also electric quadrupole interactions, etc. All this can happen. In prominent among them is the electric dipole interaction. So if you treat this as the main perturbation and use the perturbation theory in quantum mechanics, this treatment explains many aspects of Raman effect, or in general, scattering of light by molecules, such as frequency dependence, polarization, selection rules, etc. A fully quantum theory considers medium as well as field both as quantum systems. Field is characterized by electric and magnetic fields E, B treated as non-commuting operator. Field is also in fully quantized theory, field is a distributed system, and like any other quantum system, this too is characterized by like the position and momentum variables. The corresponding variables for electromagnetic fields are these E and B. The field observables are the energy, momentum, angular momentum, etc. So quantum field theory considers electromagnetic field also as a quantum system, and the quantum systems, as a quantum system, the field exists in various states. All these states form what is called the state space of the system. The electric and magnetic field variables, they act as operators and they cause transitions from one state to another in this state space of the electromagnetic system. The field Hamiltonian suggests, so if you write the Hamiltonian for the entire field, it suggests that there exist states of definite energy. Like for a particle or hydrogen atom which has got various energy levels, an electromagnetic field also has various energy levels, and corresponding to each energy level there is a state. So these are also called the Fock states of the electromagnetic field. The field can undergo transition from one such state to another during interaction with others. So when the electromagnetic field interacts with a material medium, so energy transitions occur. So taking the energy from the system or giving away the energy, the quantum state of the electromagnetic field changes from one to another. So you can see that if that is the way the electromagnetic field also behaves as a quantum system, there must be a ground state for the electromagnetic field. And this ground state corresponds to no, energy as such. That is the zero energy state of the electromagnetic field. The next nearest energy that the electromagnetic field can have, or the first excited energy of an electromagnetic field, that is referred to as a photon. So the field, if somebody excites a field from the ground state to the first excited state, the electromagnetic field, earlier it was in ground state, now is in the first excited state, and this state of the electromagnetic field indeed behaves as a photon. You can excite it to such single photon states. You can also excite it to a state where there are two photons. So these are the energy eigenstates of the electromagnetic. So the quantized electromagnetic field in this first excited state behaves as a photon. So I'm spending some time here to tell you that although quantum mechanics, as discussed at the Schrodinger level or at the Dirac level, both relativistic and non-relativistic quantum mechanics. The notion of light, although it was known in 1900 by Max Planck that it consists of packets of energy, the exact manner in which one can represent electromagnetic radiation was not known. In any effect such as photoelectric effect or even Compton effect, one would look at the energy aspect and say that, so if there is a photon, we will only take the energy part of it, and they would consider the energy equation. But if somebody asks how exactly you used the photon in your theory, right? Neither in non-relativistic quantum mechanics or in relativistic quantum mechanics, the notion of photon as a physical entity is represented there. So that is why the field theory came, and field theory suggested that the excitations of the electromagnetic field themselves are these photons. So this treatment where you say that a quantized electromagnetic field interacts with a quantized material system, that treatment can explain Raman effect in all its glory. In fact, if you look into Sakurai's book on advanced quantum mechanics, he explains Raman effect using this fully quantized theory. Of course, the deductions of that are in agreement with the semi-classical theory, all right. But however, if you consider still more advanced effects such as hyper-Raman scattering here and very high intense Raman spectroscopy, neither classical theory nor the semi-classical theory helps you to understand. Such phenomena are beyond the scope of those two levels. So the fully quantized theory can explain Raman effect and all the advanced studies or effects that people have seen using Raman scattering. However, if you are just interested in looking at how the frequency changes, so I am again telling you that classical theory itself is enough. However, suppose you are interested in knowing the selection rules and others, you will have to borrow something from quantum mechanics and put it into classical physics and talk about classical or selection rules. It is so even in semi-classical theory that it goes beyond semi-classical theory and tells you more about the interaction between field and the material medium. But the full justice is done using fully quantized. So let us come back to the semi-classical treatment. The incident radiation is mainly assumed to be electric dipole type. H is given by P dot E, right? Maybe I have missed a minus sign here. Minus P dot E. P is the dipole moment and E is the electric field of light. So to put it classically, as the electric field, as the radiation falls on matter, the electric field influences the charges inside this matter. So the negative charges tend to move towards one side and the positive centers of charge move to the other side, thus creating a dipole. For example, in the case of hydrogen, in the normal state, the positive charge center and the negative charge center are at one and the same place. Therefore, there is no dipole moment in the normal state of the hydrogen. However, when you put it in an electric field, and the electron drifts to one direction, classically looking at it, and the proton drifts to the other direction, thus creating a separation between the charge center, and that behaves as a dipole. So if you use that dipole interaction here and then put it into perturbation theory, then perturbation theory suggests that there can be transitions between the energy levels. This passage consists of two contributions. The scattering of light consists of two contributions. So as you can see here, first there is an excitation from a specific molecular energy level to an intermediate state. I want you to agree with me or appreciate here some concept which is not often mentioned in our textbooks. In our textbooks, it is said that when light enters, the molecule picks up this energy from one and goes from one of its molecular levels to another molecular level. But strictly speaking, perturbation theory tells that no. Initially, the molecule will be in certain energy levels. When light of certain frequency falls on it, look at the energy of this level and look at the energy of the incident radiation. If you put together these two may or may not correspond to another molecular energy level. So, perturbation theory says that the molecule initially is in certain specific molecular energy level, and at that instant when light falls on it, this undergoes a transition to an intermediate state where it is not necessarily a definite energy level, but soon from that intermediate state, the system, the molecule comes back to certain other specific molecular energy. So as you can see in the figure here, so the electronic or the molecular level initially is somewhere here even. This is a very well, argued out level of that molecule, say, quantum mechanics, solving Schrodinger equation for that molecule, you would have got this level. Maybe it is the rotation level or the vibration level or the electronic level of that molecule. This is a specific molecular energy level. So incident light falls on it, and then this molecule undergoes a transition to certain virtual level. So this is called a virtual level. This is not a single definite energy level always, right? So it will get contributions from all the energy states. That's what one says. It does not exist as a realistic energy level, but it gets contribution from all states. So this happens because if you write the perturbation term there, then this contribution to this process is from all states. There is a sum over all states. So all the states contribute to this process, and again from here it comes back. It may come back to certain E2. So finally the molecule sits in some other specific molecular energy level. So what I am trying to say is, before in radiation comes, the molecule is in certain energy level, and once the radiation falls on it, and in the next process, this radiation and the molecule together go into a virtual state, and then the molecule comes back to certain other specific energy level. So the scattered light is the light that you get when the transition takes place from the virtual level to the specific molecular level. So that's what I have written here. An excitation from a specific molecular level to an intermediate state, a de-excitation from this intermediate state to a specific final molecular energy level. Right? These are the two processes that take place here. So coming to Raman effect, in the case of Raman effect, what may happen is, as you can see in this figure, the molecule may be in certain level E2C. When incident radiation falls on it, from E2, it goes into a virtual level, as you can see here. And from the virtual level, it can come back to any of these states. Suppose it comes back to E1, which lies below this E2. E2 was the former energy level. Then this energy gap is more than this energy gap between E2 and this, right? So rather, this radiation that comes during this process will have more energy or more frequency than the incident light. Or once during the de-excitation process, it may come back to the same level, molecular level E2, in which case there is no change in frequency. Or it can, after de-excitation, you may find it in E3, E3 which is above E2. Therefore, the radiation now has less energy or more wavelength or less frequency. So these constitute the Stokes lines. This is the Rayleigh line, unmodified line, and this is the anti-Stokes line. So Raman effect involves all the three in a single system. And here, this photograph I have taken from, I think, the book by Long, a wonderful book on Raman effect. What a nice treatment he has given in that book. I think even if you are in BSc, you can pick it up and start studying from page 1. Very neatly written book on Raman effect and many other aspects of Raman. So this is what Krishnan and Raman both found out. So this is when just the incident lights is photographed. No, it has not been sent to any solution. But once you send it to solution, so you see that this unmodified line continues, and you see that there are Stokes lines which have less or more wavelength or less frequency, and these are the anti-Stokes lines which are not so intense and whose number is also not as good as in this case. Of course, this weak intensity happens to arise from the distribution of population in the various levels. As you go up in the molecular energy level ladder, you see that less and less molecules are present in higher and higher level. So that causes certain, the anti-Stokes lines to be less in number as well as in intensity. So all that work which Raman did was in IACS and in University of Calcutta. I think I am coming to the end of my lecture. So Raman also left Calcutta and came to IISc, Indian Institute of Science, Bangalore. Till 1933 he was in Calcutta and then came to IISc Bangalore and served as its first director till 1937 and as head of physics department till 1948. He had a long innings in IISc also. In fact, he did contribute a lot at IISc. A new physics department came into existence. Some of the existing departments were reorganized. He took steps to establish a central workshop for fabricating precision instruments. He gathered a team of talented students and started doing high quality research in many fields of physics. Raman wanted to initiate basic research in fields like quantum mechanics, crystal chemistry, and vitamins and enzyme chemistry by recruiting outstanding faculty. After his service in IISc, Raman built his own institute. Even today, it is going on the footsteps of Raman, expanding its activities. Raman came here and he started his own research activity in this Raman Research Institute. I have shown this photograph. Most of you have seen this, I suppose, but I would like the youngsters among the audience to make a visit if you have not made. And as a teacher, I used to always tell my students that every student of physics, or in general, every student of science, should go to Raman Research Institute and enter the museum of Raman. I think there are 8 rooms. Each room has a collection of what all Raman was interested in: musical instruments, butterflies, so many others. So fascinating to visit, and also the spectrometers and others he used at that time. It was so difficult at that time to get very strong beam of light. So all these are kept in this museum. There are 8 rooms, I suppose, and the 8th room is a wonderful room containing like fluorescent materials which shine once ultraviolet is passed on. You will be asked to stay inside the room, in this room, and lights are switched off, ultraviolet light is shown, and after some time, you see all the crystals there glowing like anything. And that is a rare sight, wonderful sight. And I'm sure that a youngster going there and visiting this would soon change his mind and try to follow Raman's way of life, getting into science and doing research. So that is about Raman's Research Institute. Raman's accomplishments, and he had 475 research papers, 5 monographs on various topics, Nobel Prize winning work, Raman effect, major discoveries in acoustics, ultrasonics, optics, magnetism, and crystal physics. He established the Indian Academy of Sciences, Bangalore, and the Raman Research Institute, 1948. He gave 19 radio talks later that was brought into a book form, the New Physics Talks on Aspects of. Raman got many awards: Curzon Research Award, Woodburn Research Medal, Matteucci Medal, knighted by British, Nobel Prize in Physics, Hughes Medal of Royal Society, Franklin Medal, Philadelphia. Our own country awarded him Bharat Ratna. Russia also gave him Lenin Prize. And other tributes to Raman. National Science Day on 28th February is celebrated all over India. Postal stamps have been released in 1971 and 2009 featuring Raman. Several roads in India have Raman's name. Several universities are named after Raman. A lunar crater is called Raman crater. Raman Science Center is established in Nagpur also. Devices, processes, and mechanisms named after Raman. Raman effect, Raman scattering has seen a phenomenal growth. I did not talk about the significance of Raman effect. Most of you know all that. The most useful thing happened in chemistry. Chemists have been using Raman effect, Raman scattering, because I think Raman effect gives you, tells you about the signature of a molecule. So you can understand the structure and behavior of a molecule. Raman effect and Raman spectroscopy has grown and branched into several things. I have picked up here coherent anti-Stokes Raman spectroscopy, inverse Raman effect, Journal of Raman spectroscopy is a journal purely meant for Raman spectroscopy, Raman amplification, Raman laser, Raman microscope. I have no idea of what Raman laser is, but some of you can find it in this one. Laser Raman spectroscopy is a major area on which there are several books already present now. So at the time of Raman's effect discovery, light was strong light was not available except the arc light and others. Nowadays, lasers are being used, and there are very many processes like the hyper Raman spectroscopy, second hyper Raman spectroscopy, third hyper Raman spectroscopy, etc., where you can see some novel effects being explored. So rotating polarization, CARS, coherent anti-Stokes Raman scattering, I think. CARS, yes, Raman spectroscopy. UV Raman spectrometer, spatially offset Raman spectroscopy, stimulated Raman adiabatic passage, surface enhanced Raman spectroscopy, tip enhanced Raman spectroscopy, transmission Raman spectroscopy, and X-ray Raman scatter. I think I will conclude with this photo, Raman's enthusiasm that is showing maybe its own effect to the spectators and the audience or fellow research students there. I am really enthralled by the enthusiasm that you can see in his face. So Raman represents that kind of a personality which created a miraculous change during that part of history. I hope youngsters and scientists and we all should follow at least a part of what Raman had and follow him to develop similar attitude. The country is in dire need of such an attitude. I conclude my talk by giving these references directly along the Raman effect. This is the book I mentioned. Very nice book, very self-contained book. I'm sure you will love reading it. And of course, G. Venkatraman's book, you will get minute details about Raman and many aspects of Raman, apart from his actual research, his confidence level, his ability to encourage others, his confidence in his level of research and all. P.C. Deshmukh's lecture is available. It was a talk given to high school student, but that also contains good information about life and works of C.V. Raman. And of course, Nobel Lecture Physics Series, right? There also you find Sir Chandrasekhar Venkat Raman, more about his effect. This has been brought into a book covering all Nobel lectures between 1922 to 1941 by World Scientific Company. So far I have talked to you about Raman effect, and I must thank the head KSTA for giving me this opportunity. Thanks to Sri Ramesh, CEO, and Sri Umesh of KSTA. Thanks to Mr. Abhishek for suggesting my name for giving this talk. Thanks to all the viewers. Thanks, one and all. So I conclude. If you have any doubt.
Yes, can we take one or two questions, sir, from participants?
Yes, right.
Sir, it was a very enlightening talk. Thank you very much. Very scholarly talk. Indeed, many of the things I was not aware. Because of your talk, I was able to grasp something of Raman effect. Thank you very much, sir. I am sure participants would have got sufficient information to broaden their horizon on Raman effect. Very grateful to you, sir. Thank you.
Thank you, sir. Thank you.
Please take over, Mr. Umesh and Mr. Abhishek.
Sure,
Yes,
sir.
sir.
Thank you,
Thank
sir.
you.